Hi, in this video I'm going to go over the reasoning behind the I minus Q inverse formula for substochastic matrices that I talked about in a previous video and we used to determine some stuff about how many expected flips we have to do before we see some sequence of results from our random variable for, say, a coin. So I guess this is mostly going to be, some keywords, right? So we got coin flips, probability, expectation. We're simulating things, kind of. We're going to be using some state machines, Markov chains, transition matrices, linear algebra, and this is something that you might see on a quant interview. Probably not as in-depth on the math as this, but the question in general does kind of cover that material. So again, in that previous video, we used this identity to avoid solving a system of linear equations, which was I minus Q inverse, and then summing those rows of that matrix by multiplying by the one vector. So we avoided going too deep into the details in the moment of that video, but this video is for people who are more interested in how that formula works. What is a substochastic matrix? What are transient states? What is an absorbing state? And really, we go into some linear algebra stuff, so if you're not very familiar with linear algebra, maybe this video is not for you. If you aren't, maybe you can still follow along, but you may have to do some research in your own time to kind of catch up a bit. So again, from last time we had this example where we were trying to figure out the number of expected flips before we saw the sequence heads, tails while flipping a coin over and over again. So we had the state machine, right, where we had a start state and we were flipping, and if we saw a tail, then with a 50% chance, right, that's what the 0.5 is, then we would stay in the start state. We saw a head, we would go to the head state. We saw another head, we would stay in the head state, and we saw another tail, and then we would be in the heads tails state, and then we would just stay there, right? So we saw that we could translate this state machine into a transition matrix, this one, and that is corresponded to a matrix QR01, where this is, some vector of zeros, this is some vector of, possibly non-zero, but less than 1 numbers, and then this was the substochastic transient state matrix, right? So that's this 0.5, 0.5, 0, 0.5, and then this is the 1 from the single absorbing state. So let's go into some more definitions here. So remember, we called Q that substochastic matrix of transient states. We say a matrix is substochastic if all the entries are less than 1, and the row sums are less than or equal to 1, with at least one non-1 row sum, right? So here, Q is 0.5, 0.5, 0, 0.5, right? So all the numbers are less than 1, and this row down here is 0, 0.5, and this row does not sum to 1, right? So we're always going to have one of these if we look at our transient matrices, because you have to, first of all, there are no absorbing states here, which mean that there cannot be a transition with a 1 in it, a self-transition with a 1 in it. And we do have to leave eventually, right? So not all the rows can sum to 1. Otherwise, we would just stay hopping around inside of this square matrix, and we would never exit. Next, we've got transient and absorbing states. So we say a state is transient if it's not guaranteed that we'll always come back to it infinitely many times if we kept choosing states at random, right? So in our example, start and H are transient states, right? Because it's not guaranteed that we'll ever come back to the start once we start hopping around, right? Like, as soon as we go to H, we're never coming back to the start, right? So it's not guaranteed we'll keep getting tails over and over again. Similarly, for H, it's not guaranteed that we'll keep getting heads over and over again, right? If we get tails, we're out, right? So these are transient states. But HT is an absorbing state because you can get stuck there, right? So eventually, in the long run, we do get stuck there. The question is really just like how long until we do get stuck there? How long until we get absorbed into this state? And then you can never make it back to those other states. So now let's go a bit more into transition matrices, right? So last time we said that this formula would give us the expected times between transient states, like start and H, and absorbing states like HT. So the reason for this lies in what happens when you multiply the transition matrix by itself. So to kind of build this intuition about the meaning behind the transition matrix, Let's look at this example here, right? So we have states A and B. A with, if we're at A, there's a 75% chance that we go to B. B, there's a 75% chance that we stay at B. B, there's a 25% chance that we go back to A, and A, there's a 25% chance that we stay in A, right? So as you can kind of like get the general idea, like most of the time we'll be hanging out at B, right? Because most of the time from A we're gonna be going to B, and B will generally stay at B. But it's also possible that we go back to A, right? So here's the transition matrix for that. Remember, the rows indicate where we are coming from, and the columns indicate where we were going to. In this example, is actually not very relevant because it happens to be symmetric. But yeah. So let's look at what happens when we multiply the transition matrix P by itself. So P squared, right, when you multiply this matrix by itself, we get this matrix. Note it's still symmetric, and it looks like all the numbers are kind of getting a bit closer to each other. Again, they're definitely getting closer to each other, and again and again and again. And eventually you can see we're getting very close to 0.5 in all of the states, right? So clearly as that increases, P to the n goes to 0.5, 0.5, 0.5, 0.5. And the intuition that we can get from here is that the entry, like each entry in this matrix, right, where for row I and column J, contains the likelihood that you go from state I to state J in n steps. So the likelihood that you end up basically in this state, starting at this row state after n steps, right? So this makes sense for our two-state example because we're going to be hopping back and forth. And in the long run, the higher chance that you tend to be in B versus A, it becomes, it kind of ends up going away, right? After a certain number of steps, the probability is pretty much the same that you're in either one. And after infinitely many steps, like it's 50-50 chance, right? So, or after some like very large number of steps, right? Maybe like after omega steps, right? You could say like, okay, we're going to be 50-50 chance we're in A, 50% chance we're in B. So it should make sense here because, again, each state ends up being equally likely to transition to the other, or really you're equally likely to be in either state. So what about when we want to determine the expected amount of time spent in a given state in the long run? So maybe if we add up all the probabilities that we are in a given state after a certain number of steps together, right, we'll get the total amount of expected time spent in that state. So if we have some matrix of transition probabilities, right, so then like our matrix P from before, then if we add these to each other, right, so P maybe plus P squared plus P cubed, and so on, right, then this maybe will give us the amount of time that we expect to spend in each of the states. So that should kind of make sense. It's like, okay, well, here 25% chance that we end up here, right? 25%, maybe like 62.5% chance that we end up here after however many steps and so on, right? And so if we look at where you are likely to be and we kind of sum that over every time interval, then it's like how much time you're spending there, kind of, right? I'm not sure how much sense that makes, but it's kind of like the intuition behind this, where we get this formula, right? So we have this identity matrix plus P squared plus P cubed, etc. The identity matrix comes from the fact that if you start in a given state, then you'll always be there for like at least one step. Hopefully that kind of makes sense. So intuitively, the diagonals should be like 1. All right. So now this doesn't always converge, right? So this series, as we go to some large n for the power of the transition matrix, doesn't always come to some finite number. So in our example, we had P to the n approaching this 0.5, 0.5, 0.5, 0.5, right? That's not approaching 0. So it does not converge, that series. And if we just keep adding those over and over again, you'll just get like infinity, 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 right? So this is not very useful. So if we're going to use this identity, we better make sure that it actually does end up converging. So this power series of matrices actually has a name. It's called a Neumann series. And you might recognize this series as being kind of similar to geometric series if you learned about those in high school. So just a kind of overview of geometric series, they're the sum of an infinite number of terms, like AR squared, AR cubed, where A is some like constant coefficient, and then R is some constant common radius, or sorry, this should be ratio, some common ratio R, where we just keep multiplying the term by R over and over again, and we just add up all the results. So as an example, like we can look at 1/2 plus 1/4 plus 1/8 plus 1/16, etc., etc. You might know this from Zeno's paradox, right, where like Achilles is trying to run and he runs, half the distance between where he is and the finish line every time. And does he ever reach the end? Well, apparently at infinity he does, right? And we have this formula A over 1 minus R if the common ratio is less than 1. The absolute value, the magnitude of the common ratio is less than 1. And this series, it ends up converging to this value. This is a well-known result in geometric series. If you want to look at the proof of this, do I go into? No, I don't think I really go into depth on why that is, but there are plenty of videos on YouTube that do, so go ahead with that. All right, so similar to geometric series, we can think of Neumann series as converging when the common ratio of the matrix is less than 1. So this is a bit of an interesting concept, right? Here, obviously the common ratio is like where we go from, 1/2 to 1/4, like, okay, yes, we're multiplying by 1/2, right? So the common ratio ends up being 1/2, right? This is 1/2, this is 1/2, this is 1/2. That's very obvious. But when you're looking at matrix, things end up being like a little bit less cut and dry. It's like, okay, well, what is the common ratio of this matrix? It's not just one number, right? It's multiple numbers. So 0.25, 0.75. Yeah, right? Like, what's going on here? How do we get from this to this, and then this to this, and so on? Is there really like some kind of common ratio here? So yeah, there is, and we'll talk about it in a bit. But so the non-transient matrices, like the one that we saw above, will always reach some steady state, right? So the transition matrix power is never going to actually converge to 0. So this is something that is going to cause us to not actually have this converge. Our common ratio, you can think of it like that, is going to be above 1, right? But this changes for transient substochastic matrices, where we know that will always end up in absorbing state. So in our original example here, right, we are always going to end up in HT, regardless of like eventually we'll always end up in HT, but we'll always see head and then tails. It's just, law of large numbers and whatever. It's going to go to 1, the probability, and we're always going to end up there. So we're always going to be leaving this transition matrix, right? So the probability that we stay here in the long run is always going to go to 0. So that's the intuitive explanation of why that's the case. So, why our q to the n is going to go to 0. So for transient substochastic matrices, we'll always end up in an absorbing state, so our limit is always going to go to 0. And as for like some more convincing argument, there's a paper that I'm going to link in the video description on why substochastic matrices have spectral radii rho less than 1. So spectral radius is the maximum value of your eigenvalues, maximum magnitude of your eigenvalues. And you can show that it's less than 1. There's a paper that I'm going to link. And I'm also going to link some posts online showing why, if the spectral radius of a matrix is less than 1, then the limit actually, as that matrix, the power goes to infinity, ends up being 0. So intuitively, you can actually kind of look at the eigenvalue decomposition here to see that, as n goes to infinity, the power of the eigenvalue matrix will go to 0. But again, so this is a bit too much in depth. And you'll see some stuff on matrix norms also. But, as for like why Neumann series can converge, if any of the matrix norms is less than 1, then you can look at that. But I think this is a lot more intuitive of a way to look at it. And you can say more stuff about eigenvalues for transient substochastic matrices than you can maybe about like matrix norms. It's not as easy of a jump. All right, so let's go back to the Neumann series again. Now we know that it converges, right? So let's think about how does this turn into our formula, I minus Q inverse. So remember our geometric series analogy. So for a geometric series with a coefficient A and common ratio R less than 1, we had this formula, right, where the sum, this should also really be of like R to the n, or like A R to the n, but basically this sum from n equals 0 to infinity of AR to the n was equal to A over 1 minus R. So in our Neumann series, the equivalent of the common ratio is the matrix itself, right? Because we're multiplying by the matrix itself over and over and over again. And the analog of 1 is, of course, I, while the analog of putting something the denominator of a fraction, right? So like the dividing idea is inverting the matrix, right? So this is kind of similar to A over 1 minus R, where A ends up being 1 here, right? So we don't really have a coefficient that we're, some kind of scalar coefficient or something here. We just have like 1 over 1 minus Q. In this case, that would be like I minus Q inverse, right? So this is the direct analog of what we have in geometric series. And if we just want to confirm that this is actually what it goes to, and I'm pretty sure there's a similar kind of proof for why geometric series converge to what they do, but we can just multiply both sides by I minus Q. And when we do that, things cancel very nicely. And we get, I minus Q, and then Q minus Q squared, and then Q squared minus Q cubed, etc. So you can see like these terms will cancel, these terms will cancel, and so on until we get like some very large Q to the n, some very large n, right? And then Q to the n, as we saw, it's going to converge to 0. So it ends up being I equals I, which is correct. So kind of to go over, to summarize this a little bit. Summing these long-run transition probabilities gives us the long-term number of times that a state is reached. Right? So in the long run, we'll reach a state that many times. If we look at the number of times a state is reached in a transient substochastic transition matrix, like we saw, across all possible sources, by summing those rows by multiplying by the one vector, we'll get the amount of time spent there in the transient state matrix in the long run. And then since the amount of time spent in the transient state matrix is the same as the amount of time that until an absorbing state is reached, this is exactly the expected number of steps until the absorbing state is reached from the transient state, right? So to kind of go over that again, right? Basically, we're determining the amount of time that is spent in states like, in this example, start and H, right? The amount of time that we spend in our substochastic transient matrix, Q, is going to be like one less or really like equal to the amount of time before we get to this 1. So before we get to HT. So the amount of time we spend in start and H is exactly the amount of time that we spend in HT. And you could say like, okay, well, maybe it's 1 minus that. Well, that's why we're adding the identity matrix in our formula, right? So that should be a bit intuitive, hopefully. And then we can simplify this matrix sum, right? So like I plus Q squared, all the way down to I minus Q inverse due to various properties of Q. And then, we get the row sums by multiplying by the one vector. And then looking entry-wise at this, right? So we get some vector result. We can get the expected number of steps between each transient state and the absorbing state. All right. So thanks for watching. I put sources and material for that might be of interest in the video description. I know that the jump from the transition matrix probabilities to the power series being the expected number of steps was there's a pretty large gap there, pretty large jump. So let me know in the comments if you have a better intuitive explanation, because I know that wasn't as maybe intuitive as it could be. And if you haven't had a chance yet, make sure that you watch the original video on coin flip sequences. It'll put this in context, and I think also that is a lot easier to parse compared to this video, especially if you don't have the background on this one. So that's it, and thanks for watching. See you next time.